one simplification is to go from 3 dimensions to 2 dimensions. So, we have looked at examples such as fully developed flow in a parallel plate channel. We have looked at flow through a circular tube as examples, a layer of a liquid film flowing down an incline. I have already said that I will expect you to remember Navier-Stokes equations, 2 dimensions, incompressible, in Cartesian coordinates. In cylindrical, I'll give you the concerned expressions, whether it's a quiz or the final exam. Now, that doesn't mean you should not be aware of it. Please use those equations and solve. So, can I request you to settle down quickly? Okay, so please be familiar with these equations, look at the full form, learn to simplify them to the extent possible. That means, if I tell you some velocity distribution is independent of the radial coordinate, let us say I do that. What does it mean? It means that the derivative of that quantity with the radial coordinate will be 0. Okay, so we will be able to implement simplifications of that type. I have sent you a handout on this topic. I hope you have seen it. Please do take a printout and then use those expressions as your starting point for further analysis. There is always this question, can I solve these equations completely? In the analytical framework, the answer is no. So, we still await a general solution of Navier-Stokes equations, but there are specific solutions to the simplified forms of Navier-Stokes equations, but one can also obtain approximate solutions of the full Navier-Stokes. So, try to distinguish between these two: approximate solutions of full Navier-Stokes, exact solutions of approximate Navier-Stokes. So, Cartesian will be x, y and u, v are the velocity components. Cylindrical could be r, z, in which case the velocity components are u, w or r, theta. These are the components. The moment you have curvature in the coordinate system, you will have additional terms arising from the derivative del operator. I think some of you called it the gradient operator, because when you differentiate with respect to r and theta, the unit vectors E r, E theta are no longer constant. They give rise to curvature terms, and they will all be of the form 1 over r times something, and as r approaches infinity, the curvature terms go away and you get back Cartesian coordinates. So, what I have not done is go from coordinate free form to the governing equations in curvilinear coordinates. That is an aspect of vector calculus, leaving it to you as let us say, let us call it self study. Yeah, so this is the handout that was sent to you. Two-dimensional form of Navier-Stokes equations. This is the initial part, Navier-Stokes in coordinate free form. So, for bonus the stress strain relationship is also given, sigma equal to minus p delta I j plus 2 mu epsilon dot I j. This is all in coordinate free form. So, so maybe I should have written this as half of del u plus del u transpose. That is the form I wrote in the during the lectures. Then we move on to Cartesian coordinates, x and y with u and v as velocity components, suffixes indicating partial differentiation. So, the stress sigma I j, the stress tensor, will have components sigma x x, y y, x y, y x, but x y is equal to y x. So, these are the expressions. Most of the time you have to evaluate sigma at the wall. So, you have to find out how the derivatives vary at the wall and evaluate them. So, u x plus v y equal to 0 is mass balance, then x momentum equation, y momentum equation. So, the basic unknowns in 2 dimensions are u, v and p, 3 unknowns, 3 equations. But for fully developed flow, we managed to reduce these 3 equations to 1. If you have 3 dimensions, you will have mass balance and 3 momentum equations corresponding to 3 components of velocity. Okay, so, sometimes people ask, what is so special about Navier-Stokes equations? It is special because it is sort of complicated. It is a hard system of equations. Why is it hard? First of all, these equations are coupled. You can see it is not as if you have 3 equations and the 3 are standalone. The mass balance contains u and v. Momentum also contains u and v and pressure. The other momentum also contains u, v and pressure. So, you have to solve them simultaneously. Okay, so, the 3 equations, anytime you have coupling, the complexity goes up, unless you can decouple very quickly. But here there is no obvious way in which you can decouple the governing equations. So, that increases the complexity of the problem, and you can't predict what the solution is going to be offhand, but then you know from your experience the same equations hold for a whole range of devices, natural phenomena and a variety of scales, small scale, large scale. So, that is one reason why the system is complicated, that is coupling. In that liquid layer problem, you had liquid layer and air. So, you had in principle you had to write equations in air and equations in water. So, you have two fluid media and you have to write this system twice, once in air, once in water. So, the complexity can become much greater very quickly. The second reason why it is complicated is because of the non-linearity. This may not be immediately apparent to you, but this system of equations is non-linear, while the problems you have or the theory you have studied, this fat book of Kreyszig, it is becoming earlier. 20 years ago it was much thinner, it is becoming fatter, really fat. But it is still dealing with linear problems all the time. So, what is linear, what is non-linear? Please check up those basic books on mathematics. So, when you talk of analysis, engineering analysis, linear algebra, functional analysis, this is a linearity that is built into the background. An equation, I think we had in the case somebody mentioned heat equation, fully developed flow with the time derivative, we were able to solve because of the linearity of the problem. Overall, in a linear problem, you do not see the unknown variable multiplied by itself or its derivatives. So, that is sort of a quick and dirty way of ascertaining if the problem is linear or non-linear. So, suppose you had just u x x plus u y y equal to 0, the Laplace equation. U is your unknown and u is appearing with its derivatives. There is no product of u with itself, but look at the left hand side, you have u multiplying the derivative of u. More than that, it is a v multiplying the derivative of u. So, that jacks up the complexity, the extent of non-linearity of Navier-Stokes equations. If you have to create a scale on non-linearity, the Navier-Stokes equations rate very high on the non-linearity scale. This is another reason why the system of equations is complicated. So, that is the motivation for us to simplify. So, we are looking at special solutions. We are not going to address complexity, we will try to look at problems that can be solved, so that we gain some insight into how flow phenomena take place. So, I gave you in this handout, I have given you Cartesian, 2D Cartesian, which I expect you to remember. Then we have R z. Okay, so R z, you have sigma R r, sigma z z, sigma R z, and now you can start seeing the presence of curvature terms, which are all 1 over r times some quantity. And if you take the limit r approaching infinity, this will go back to your Cartesian coordinates. And overall, the complexity of the governing equations will increase further. What happened? I think this that I do not know if it is because of the projector. There appears to be some here. This document is not projected properly. I have to check that here. Then we have r theta. So, r z had lesser impact of curvature, r theta has even more impact. can see that the equation looks much longer than what you had for RZ. I mentioned last time that if you work in coordinate free form, then those very special forms of acceleration such as centrifugal and Coriolis will automatically emerge. You do not have to add them separately. So, it is a unified formulation of the governing equations. And where will you find the acceleration terms? On the left hand side with the inertia terms, mass times acceleration. That is where you will have acceleration defined in a curvilinear coordinate system. Terms such as uv divided by r, v square over r. Okay. So, in general, what would you do? In general, solve Navier-Stokes equations with boundary conditions. That is where the geometry of the problem comes in. Flow through a tube, flow over a cylinder, that is where you apply boundary conditions and specify the geometry of interest. Once you have velocity distribution and pressure distribution, go back to the constitutive relationship and get the stresses, integrate stresses on the surface of the object or any other portion of the flow field and get the complete force acting on it or complete moment. In other words, derive the quantities of interest from the local distribution of the flow field and the pressure field. So, please handle this document for solving problems, so that if suddenly if you see these equations in the exam, at least it would jack up my blood pressure a little bit. Okay. So, and I am quite happy I do not have to appear for the exam. Okay. So, maybe I should revert to what happened to the PDF. So, we were looking at an example of concentric cylinders, one cylinder, outer cylinder is given some rotation. And a velocity field is established in the gap between the two cylinders. We expected flow to be fully developed in the gap. I was trying to explain last time that anytime you make an approximation, it is called a modeling step. Okay, so modeling is mathematical modeling. You do not get any other ideas. Okay. The modeling step helps you simplify the governing equations. So, what was the simplification? That the flow was fully developed. In that context, it meant that velocity was not changing in the theta direction. Substituting that result in mass balance, this is mass balance. Flow is not changing in the theta direction. That gave us this equal to 0, which gave us u equal to 0, because the boundary conditions are u equal to 0. Right? On the walls, the normal u is the normal velocity component on that surface. So, u is 0. When you put that u equal to 0 in this equation, in the radial momentum equation, unlike a flow in a parallel plate channel, you got a non-zero pressure gradient in the radial direction balanced by the centrifugal forces. So, if you force the fluid to rotate, you will generate a pressure gradient in the radial direction. This is similar to pressure gradient appearing in a gravity field where pressure is balanced by gravity. Here you do not have gravity, but you have centrifugal forces. Second equation was, then we also reasoned out this derivative to be 0, u 0, time derivative 0, derivative with theta 0. So, this entire left hand side was 0. So, it was a non-accelerating flow field. So, we had a portion of the right hand side being equated to 0. So, let us So, continuing with that example, this gap is filled with oil R1, R2, and we got, so we got u and v as the velocity components. So, I am writing the governing equation for v, u is 0 and subject to these boundary conditions. So, it is a second order. So, the fully developed flow approximation linearizes the Navier-Stokes equation. So, one way of simplifying Navier-Stokes is to look for ways and means to linearize it. Okay. You can reduce its dimensionality, okay, 3D to 2D to 1D. You can try eliminating time derivative by saying I am looking at only the steady part of it. And then next is you try to linearize it. These are options available to simplify. So, I am sure you know of many different approaches for solving ODEs of this type. One approach is you can combine the second and the third term, 1 over r V r minus V over r square can be written as what is it? V over r. And then integrate once. So, I will give you the general form. So, C1 and C2 are constants of integration to be found with reference to boundary conditions. So, this is the general form. So, plenty of special cases. What if R2 goes to infinity? You have a cylinder rotating in an infinite fluid medium. Okay. What if R1 goes to 0? That means there is no cylinder. Then it will reduce to solid body rotation. What is it called? Rigid body rotation. That means velocity will be equal to omega r. So, all those special cases are contained in this result. A very important application of this problem is in finding viscosity itself. So, let us say you want to find the torque or the moment acting on the inner cylinder. So, you will find This is a portion of the inner cylinder. So, the moment of sigma RR on the inner cylinder is 0, it passes through the origin, and sigma r theta, so you can refer to the notes given. The sigma r theta has a longish expression So, this I have picked straight from the notes given to you. Now, this derivative of u itself is 0. So, its derivative with theta is also 0. This is 0. What about V? V on the surface, it is a stationary cylinder. So, V is no slip condition. So, V is also 0. So, you are left with on r equal to r1, sigma r theta is given a symbol tau wall, okay, which is sigma r theta at r equal to r1. So, this is equal to mu r equal to r1, where V is the solution given. So, look at the overall mindset, which is to start with Navier-Stokes equations, simplify, get the solution, put them into constitutive relationship, and then extract quantities of importance. So, once you know wall shear stress, you can get the torque as 2 pi r1 tau wall times r1 in units of newtons per meter being normal to the plane of, that is the z direction, which has been ignored in the analysis. Okay, now, in problems that you will be given, as well as problems given in the book, viscosity is prescribed to you, viscosity is given. But if you deal with a new medium, the question is, what is viscosity? So, this approach is often used to find viscosity. You have concentric cylinders, and then you find the moment acting on the inner cylinder by suspending it from with a torsion wire. So, the wire will twist, and you can measure the angle of twist. That will give you a measure of, it is like spring. If you elongate the spring, you can measure force, or you can compress the spring and measure force through displacement. Here it is through angular twist. So, you measure torque, and through torque you can see that tau wall, this tau wall depends on mu. So, you can find mu. So, this is a method of finding viscosity in many contexts, and it works well. Would you say you would prefer to use it in liquids or in gases? Can you use it in gases? Yes, except that viscosity of gas is very small, and the twist it is going to produce may not be measurable. But if you use it in liquids, particularly oils, the twist will be very large, because viscosity is very large. So, let us continue with our discussion on the simplification of Navier-Stokes equations. So, let us write down the equations once again in coordinate free form. Here the variables are in dimensional form. For example, u is in meters per second. If these expressions are non-dimensionalized, we have already seen some advantages of non-dimensionalization. If you remember Moody's diagram, the original relationship was pressure drop is a function of velocity, diameter, length, viscosity, density, surface roughness. But then if you cast it in non-dimensional form, the number of variables becomes much smaller. Friction factor is a function of Reynolds number and surface roughness parameter. So, non-dimensionalization helps you in reducing the relationship to compact form. You can think of it as simplification. We will also see that it can be used, non-dimensionalization can be used to simplify Navier-Stokes equations in many other ways. So, at that time we reduced the functional form given in terms of dimensions to a non-dimensional relationship through we used a method called Buckingham pi theorem. I think in your tutorial there was some Ibsen's method or something, so I should have cut it out. I think you please stay with Buckingham pi theorem. Now, the functional form is given to you. This is the functional form. It is not a generic functional form, it is a specific functional form. Now, this specific form can be non-dimensionalized. So, what is the functional form? It is the solution of this system of equations. So, let us introduce, most of the time you have some idea of the velocity, some idea of the length scale. If you are studying flow through a tube, then you know diameter is a very important quantity, that is a length scale. If you have flow over a cylinder like a chimney, again you know it is the diameter of the chimney that plays an important role. You can pick the diameter as a length scale. If you have a gentle breeze going past a chimney, then that upstream velocity becomes a velocity scale, characteristic velocity, which you can pick as capital U. What is the advantage of picking a characteristic, let us say velocity scale? So, characteristic scales. Using which you can define non-dimensional quantities such as U star, which is U over capital U. Similarly, X star is equal to X over L. The advantage of introducing dimensionless quantities is that with respect to the starred quantities, your velocity will be of order 1. You do not have to say velocity is 10 raised to minus 3 meters per second. So, velocity is 1 or 0.5. 0.5 is half the characteristic value. Okay, it is a new scale, but in the process there are no units. U star and X star do not have units. So, you can construct other scales also. Del's, this is the gradient operator will be 1 over L, I should say L, I am sorry. L times the gradient operator will give you del star. Okay. You can define time T star is equal to U T over L. And you already have an idea about pressure. So, P star will be P over rho u square. So, what you can do is now substitute for this u can be expressed in terms of u star as u star times capital U. Capital U is a constant. So, it cancels off and you get this is the dimensionless form of the mass balance equation. I have substituted for del in terms of del star, that becomes del is equal to del star divided by L, and then for u I have put capital U times u star, but those are constants. So, there is no change in the form of the mass balance equation, remains unchanged. And then if you look at the momentum equation, you will get, so now these are all vectors. I am skipping one or two steps. You have to plug in for u, substitute u star times u. For t, you substitute L t star over capital U from that expression, and then take all the terms, divide throughout, by rho u square over L, divide throughout, and then gradient of p will become del star p star. So, maybe I can show the vectors more consistently. This is, so it is a vector equation, all in terms of starred quantities. This rho mu, all of them accumulate here, giving rise to a Reynolds number, which is rho u L over mu. Okay. So, if you look at one step ahead of what I have written, this R e will be this will appear to be rho u square over L divided by mu u over L square. This rho u square over L comes from the left hand side, and mu u over L square comes from the viscous stresses term, mu del square over u, mu, right. This del square will become del star square divided by L square. Okay. U is u, capital U. So, it is the ratio of these two which gives rise to Reynolds number, rho u L over mu. So, mu u over L square comes from the viscous term. So, you may call it, let us call this V, it is a viscous force, and rho u square over L comes from the inertia term or the acceleration term. Mass times acceleration is also called inertia force, if you remember. Where is mass? It is in terms of rho. Okay. So, Reynolds number, with this formulation you see that Reynolds number is a ratio of inertia terms to viscous terms of the Navier-Stokes equations. Okay. Now, let us make one more sweeping simplification, which is to drop all the stars. So, in the book, not only this book, any other book, they will give you Navier-Stokes equations sometimes in dimensional form. If you see rho and mu, then you know it is in dimensional form. If you see Reynolds number, then you know it is in dimensionless form. Okay. So, rarely does one carry through all these stars. So, Navier-Stokes equations in dimensionless form is given as del dot u equal to 0, so, how do you know it is dimensionless? Because it has Reynolds number in it, and this Reynolds number is defined as it is interpreted as the ratio of inertia forces okay, broadly speaking. So, you have already seen Moody's diagram where Reynolds number may go from 1 to some 10 raised to 6, but I have referred to applications where Reynolds number may go from 10 raised to minus 15 to some 10 raised to plus 15, plus 16. So, the range of Reynolds numbers can be very large. And how will Reynolds number change? Why does it change so much? Mainly because, see, look at the quantities. So, you know, in gas viscosity is very small. So, in gases Reynolds number will tend to be very large. Your length scale, if you are talking about flow over an aircraft, the length scales could be 10 meters. But if you are talking about flow in a tube, it is only maybe 10 mm to 50 mm, that is the diameter. So, length scale can vary a lot. Velocities can also vary substantially. It could be just, if you think of small dust particles moving in water, that velocity could be 0.3 or 0.1 meter per second. But if you have a gust of wind, that velocity could be 20 meters per second, 40 meters per second. Okay. If you think of a jet of gas coming out of a nozzle in a propulsion application, okay, like a jet engine, a rocket engine, velocities can reach the speed of sound or even higher. How much is the speed of sound in air approximately? Huh? What? More than 300 meters per second. Okay. So, now if you study aerospace engineering, they talk of supersonic flow, which is many times the speed of sound. Then they talk of hypersonic flow, which could be 7 to 8 times the speed of sound. This is the fluid speed. Okay. So, we are talking about a very wide range of velocities, length scales. So, Reynolds number can also change substantially. So, the question is, can we simplify Navier-Stokes equations by looking at the order of magnitude of RE. So, in some problems RE may be very small. In that case, if RE is small, it tells you that viscous forces are very dominant compared to inertia. So, the momentum equation can be written as, this is an approximation, 0 equal to minus gradient of P plus 1 over RE del square U. So, this is a reduced form of Navier-Stokes equations. It is often called the Stokes equation. So, also Stokes equations, because you still have it is a vector form. There are 3 components to it in 3D plus mass balance. There is no change in mass balance. Just because RE has become very small, it does not simplify your mass balance equation. You can also think of a very high Reynolds number, RE much greater than 1, in which case viscous forces are not significant. So, you can drop the viscous term. So, here I have dropped the viscous terms. Okay. So, RE much greater than 1, I much greater than V. These equations also have a name. They are called Euler equations. So, why so many names? Because people have looked at portions of the Navier-Stokes equations, so that some quick solutions can be obtained with less effort. But I was referring to you about computational algorithms. Those algorithms work with the full massive Navier-Stokes equations. They do not work with the reduced forms. The reduced form is really to facilitate analytical solutions, but analytical solutions require linearity. Stokes equations, do they look linear? They are coupled, but they look linear. Right? There is no, you do not have the product of the dependent variable such as u with itself. So, Stokes equations are indeed linear, but the Euler equations are not linear. You have the product of velocity with itself. Okay. Euler equations are non-linear, Stokes equations are linear. So, that linearity helps you derive solutions. We will see that Euler equations, even though they are non-linear, they can be linearized. That step we will see as we go along. Now, we had fully developed flow. In fully developed flow, inertia is identically 0. Okay. So, that is what led us to the Stokes equations. So, we have to distinguish between fully developed flow, where Reynolds number is not necessarily small, but inertia is 0, okay, giving rise to Stokes equations. Okay. But in Stokes equations, we are looking at flow that may be developing. That example we will see tomorrow. Flow is developing, but Reynolds number is small. And then you have Euler equations. So, we will then move on from Stokes to Euler, start looking at the limit of high Reynolds numbers. So, let me, I think the class is abruptly it's over. So, hopefully we can keep up the